second chapter of aircraft instruments and systems. Here we're going to talk about principles of aircraft instrumentation. Okay, this is this is the second module, principles of aircraft instrumentation. Let's start at first with the measurement fundamentals. Okay, aircraft instruments are designed to measure physical quantities and convert them into usable information for pilots. Okay, physical values or physical quantities such as like the pressure, the temperature, things like that, and based on these readings they would provide alarms or warnings, or it would display what is an analog info into a readable info that can be used and understood by the pilot. Okay, let's say you have a binary system on an instrument that is electronically being displayed. It cannot be displayed as binary in the binary format as zeros and one. It should be converted like computers basically to a readable format, okay, like in an ASCII system, so that you can read real numbers and real words, okay, that should be meaningful to you as a pilot or as an aircraft maintenance engineer in order to be able to troubleshoot and to assess the performance of the aircraft. Okay, the accuracy and reliability of these measurements are essential. They need to be accurate, giving you real, accurate, precise measurements, and reliability meaning they should be reliable or trustworthy under whatever flying conditions that you are under, whether icing, whether hot weather, whether rain. Okay? Now, which is essential for safe aircraft operation. The most common physical parameters measured in aircraft instrumentation include air pressure, temperature, speed, and position. By the way, through the pressure measurement, okay, in the pitot static system, through that reading, the altimeter can actually get the value of the altitude. So the altimeter converts that the pressure differential between the pressure from the outside, okay, and the static pressure, which is the air that has been kept and sealed when the airplane was still on the ground before flying into a specific altitude. Okay, so the difference between that static air, which is the pressure at ground level, and the dynamic air during flight, that differential can get us to calculate the altitude, the VSI, during movement of the air, okay, vertical speed indicator, and what? The airspeed. So these instruments can measure that, can evaluate that, and display it in a readable format to pilots based on these measurements of the pressure, okay? Because through the difference of pressure, we cannot understand, okay, at which height am I? The instruments do that, okay? Like by changing the needle based on that pressure differential, I can actually read on the display the value of the altitude, the actual altitude, the airspeed, okay, speed of the air moving through and around the aircraft, which is actually the speed of the aircraft within the air, okay? And also the VSI or vertical speed indicator, okay? So temperature as well, speed, and position. Position is mainly based on the GPS, for example, another instrument, or position in respect to the runway when we talk about the ILS system, instrument landing system, like your position in respect to the localizer, which is the vertical plane crossing the middle of the runway, okay? So if you are to the right, you should be correct to be aligned, so that line should be at the center of the attitude indicator, and the glide slope, which is the horizontal line. If like the golden point on the attitude indicator, that cursor is underneath the glide slope, it means that you are very low, okay? You are beneath the descent slope. If this dot is above the horizontal line, it means that you are over the glide slope, so you're about to shoot the runway. Okay, so you need to adjust in a way to access the glide slope, to enter the glide slope in a perfect way, and to stay there until your final touchdown and landing. Pressure measurement. So pressure is one of the most fundamental parameters in aviation instrumentation. It is defined as the force exerted over a surface area. Okay, force exerted per unit area, and is commonly measured in Pascal or PA. Okay, you have another international system measurement unit, which is Pascal per square inch, okay, or PSI. Okay, so it would be Pascal per square inch, because the PA, Pascal, is per square meter, okay, or inches of mercury in Hg. Now, in aircraft, pressure measurements are primarily obtained through the pitot-static system. Okay, the pitot tube and the pitot-static system. Static pressure is used to determine altitude and vertical speed. Okay, so the static pressure is used to determine altitude and vertical speed, VSI, while dynamic pressure, which is the ram air going through the pitot-static tube, is used to calculate what the air speed, okay, the speed of the airplane. Pressure sensors may be mechanical, such as diaphragms and capsules, or electronic, such as piezoelectric or strain gauge transducers. Okay, we're gonna understand it better in the further slides. Now, accurate pressure measurement is critical for flight performance, okay, navigation, and compliance with airspace requirements. Errors in pressure sensing can lead to incorrect altitude or airspeed indications. So it would give false assessments to the pilots, and distort their situational awareness on whether they are flying too high, too low, too fast, too slow. These are very crucial and important pieces of information. Okay, potentially it can compromise the safety of a flight. As an example here, so let's talk a little bit about the altimeter, how it measures the altitude. You see here, this compartment is where the stored, is where we store the static air from the ground level. So the static air, which was collected when the airplane was still on the ground before taking off, before increasing and climbing in altitude and actually starting the journey, this is where the air is stored and locked within this diaphragm-like compartment. Okay, now as the altitude increases, what happens is that the difference between the pressure stored inside the diaphragm and the pressure of the surrounding ambient air, okay, at a specific altitude, this difference increases. So what happens is that the air on the inside would start pushing, dilating, because of that pressure differential. Okay, it would start extending and dilating these aneroid wafers. As it dilates, it will motorize, or it will move something, this rotor-like mechanism. This in its turn will rotate these gears that are connected to the needles within the altimeter, and hence the altimeter would, the needles would rotate, indicating a value of height or altitude based on what? Based on that difference between the external pressure and the internal pressure that is locked within this sealed compartment. This difference of pressure would again rotate this internal mechanism. I don't know what do they call it here, like a rotating gear, which is connected to the needle on the inside of the altimeter, that in its turn will display current altitude. Now, to the left, you have the VSI, or vertical speed indicator. To the right, you have the airspeed indicator, ASI. And by the way, the three of these instruments, whether the VSI, the ASI or the altimeter, the three of them depend on the pressure measurements in order to display or to give us the values, the different values of the parameters that we are after, whether the speed of the air speed, or the VSI, okay, the climb rate. Okay, VSI give us the climb rate. So climb rate, how many feet per minute are we climbing in case the airplane is climbing, or the descent rate if it's diving. And for the altimeter, it gives us the altitude. So for the VSI, because we've already explained the altimeter, how does the VSI work? And you have a common denominator, which is the diaphragm locking static air on the inside that has been locked and sealed when the aircraft was still on the ground, which is used as a reference point to measure the altitude, the ASI, the airspeed, and also the vertical climb or descent rate of the aircraft. Okay, at first, if we look, so you have the direct static pressure here. You have a calibrated leak in order to readjust the pressure of the air when you are on the ground before you seal it. Okay, now once the aircraft becomes airborne again, so what happens is the difference between the pressure of the air that's locked on the inside of the diaphragm and that which is on the outside, okay, that pressure starts, the difference of that pressure starts increasing. Now, as the airplane goes up, so the pressure of the external air or ambient atmosphere becomes so low to the point that this diaphragm will start extending, dilating. Now here it dilates and then retracts, by the way. Why? Because when it changes, if it changes rapidly, it dilates quickly to display a positive climb rate. Okay, it dilates. When it dilates, what happens is that it rotates this needle, so it will display a vertical speed, okay, a positive climb rate. And then once it stops climbing, so it will return, so it's somewhat elastic. This diaphragm will retain its original shape. Okay, now meanwhile, when it's descending, this is what happens. The opposite happens. It means that it will collapse. Okay, why? Because now the pressure, the external pressure, is increasing, so it will start becoming more extreme than the pressure of the air on the inside. Okay, so it will collapse it, which will make the needle rotate downward. Okay, so it will rotate upward for positive climb rate, which is due to the extension or dilation of the diaphragm, and it will collapse. The diaphragm will collapse, will crush, will compress, rotating the needle downward during descent. This is how the VSI works. Airspeed indicator. Now, for the ASI, how does it work? You have, again, for the pitot-static system, everything like the ASI, VSI, and the altimeter, the three of them are connected to the pitot tube. Okay? Now, for the pitot tube, it receives a ram air or like the dynamic air through that inlet. Okay? It enters via the pitot tube. And then for the ASI, it will start pushing against this diaphragm that has static air locked on the inside of it. Okay? Again, collected from the ground level atmosphere. So, as it pushes it, and this is how it works. The ram air, okay, it has a dynamic pressure, which is, by the way, the dynamic pressure, or Q, is 1/2 rho V squared. So as it pushes it, or pushes against the static air within the diaphragm, it will start rotating a lever that in its own turn, it will rotate the hand staff pinion, okay, through a gear. This is a sector here, and this will rotate, the hand staff pinion again, which is connected to the needle that will indicate the airspeed. And usually the measurement or the measurement unit is in knots. All right, it can be converted to miles per hour, but usually the official system is in knots. okay? And this is how it works. So it depends vitally on the ram air, the dynamic air being inhaled by the pitot tube. This is why if in any case the pitot tube gets like pinched or it gets stuck on something or something gets into it, it will prevent the air from moving freely on the inside, which will cause wrong measurements. Okay, it can lead to, actually, there was an air accident that led to large fatalities due to a static tube getting, I'm trying to find the correct word, it got sealed, okay, due to one type of birds that usually creates, or one type of a bug, okay, an insect that creates its nest within these types of any type of cavity, and they had forgotten to seal it, to seal the air, the pitot tube. That's why it got to that point where it led to a great accident. Temperature measurement. Now, temperature measurement is essential for monitoring engine operation, air density, because density and temperature are interrelated, especially when it comes to gas. So, when we're talking about the atmosphere, when we're talking about the engine, the air within the engine, it all depends on pressure. Okay, so pressure and temperature are correlated, and system performance. Now, common temperature measurements in aircraft include outside air temperature, or OAT, EGT, or exhaust gas temperature, which is the temperature of the air at the exhaust of the engines, okay, which is the exit of the engine. It can tell us whether the engine is overheating or not, okay. And you have the turbine inlet temperature, which is the inlet of a turbine where it's sucking the air, okay. So it is at the level of intake of the air where we're measuring the air temperature, okay. Turbine inlet temperature, or TIT. And also the oil temperature. So if it's overheated, we might be suffering from an overheat of the engine, and the engine might have a big problem, okay. So if you have an overheat of the oil, it means that there's no cooling within the engine, or there's a big problem developing, okay, depending on the scenario. So mainly the temperature of the oil should be nominal. The temperature of the EGT, exhaust gas temperature, also should be nominal. If we are going above specific limits, it means that the engine is overheating, okay? And a bigger, more serious problem can be developing on the inside. Now, temperature sensors typically operate based on changes in electrical resistance or voltage. Exactly. You see, you have what is called the thermistor, okay? Thermistance in French. Okay, the thermistor is a resistor that changes in value as the temperature increases or decreases. In other words, consider a thermistance, okay? So you have, during cold or in normal operating conditions, the material, which is, by the way, made of conducting material that is stitched together, okay? So during cold weather or normal operating conditions, when you have a low temperature, this material, the molecules of this substance are stuck together, which is a conducting substance, by the way. So the current would go easily. It would act as a short circuit, conducting the current perfectly. Meanwhile, as the temperature increases, these molecules would start going apart, like dilating, because the material would start dilating, and the molecules would start growing apart from each other, which will create more gaps. So the current will drop. The resistance against the current would increase. To give you a more clearer picture, if you imagine the temperature rising to 1000 degrees Celsius, for example, okay, what will happen is that this resistance would dilate indefinitely to the point that it will snap, it will break, which will create an open circuit. So the current going through it would be completely zero. Why? Because it became completely resistant, meaning it's now an open circuit. It's no longer allowing any current to pass through. Why? Because you have, pure air, pure void between the two connectors of this resistance. Okay? Now, of course, that would be the extreme case. However, when you have, and it can happen by the way, but even as the temperature increases, this material would start dilating more and more, forbidding more current to go through it. Why? Because the molecules are no longer intact and interconnected with each other. So less current would be going through, or the resistance value of that resistance, okay, would grow. Okay, it would increase. Now, we can easily, in such case, interpret the dip of the current to a specific level as an alarming thing, as an overheat having occurred to the engine or wherever this measurement device has been installed. Okay, so as this current decreases, you get to a point, okay, now we know that you have a very high temperature. This is when the alarm overheat, okay, would be the overheating alarm would be signaled or warning. It can be warning if this dip in resistance or dip in current, okay, increase in resistance, but a dip in current is not as serious. But when you have it snapping completely and completely cut, it means that you have a fire on board that had completely melted this resistance, okay, and you would get within the cockpit a fire alarm. So hopefully this explains it. Now, another type of sensors can be, by changing voltage. Actually, yeah, you can connect a voltage to that resistance when it opens up, or it would be connected to another thing. So the change of this resistance would also change the voltage. Okay, but it's not necessarily only this type of sensors. You can have another type which is voltage based. Okay, so when you have a change of voltage, it means that you have a change of temperature, and based on that, you would have an alarm signaling off in the cockpit, or a notification, or like a LED being set off. So devices such as thermocouples and resistance temperature detectors, RTDs, this is what we were talking about, thermistors or resistance temperature detectors, are widely used due to their reliability. So you can account for them, you can count on them to accurately describe what's happening, okay? And they have a high accuracy over wide temperature ranges, meaning that the resistance would definitely change only based on the value of the temperature it's being exposed to, which will give us a good estimation or good estimated measurement of the temperature. Okay, so it's not only for alarms, it's not binary whether you have fire or not, or you have overheat or not. No, you can get an accurate measurement of the actual temperature within the engine or within any part of the airplane when you have this kind of RTD installed. Now, temperature data influences engine control. Also fuel efficiency, because when you have an overheat, it changes things. Okay, and icing detection. Okay, when you have when also the resistance is so low, it means that you have icing. So the current not passing through is not always, or the current fully passing through the conductor is not always a good thing. If you have a maximum current, it means that it's so cold and freezing, okay, that you need to de-ice where you have placed this sensor. Okay, so the temperature data is very important. It can influence engine control during icing conditions, icing detection performance calculations, okay, because based on the EGT, for example, the exhaust gas temperature, you would assess how much is being burned, okay, if the fuel is being effectively burned, or if there's a residue within the engine, meaning that, and which can result in engine backfire. This is usually when you have broken blades stuck within the engine, which will disrupt the airflow, forbidding the airflow from moving freely within the inner parts of the engine. So the fuel would not be fully consumed or burned up, which will cause an engine backfire. So it will fire on the inside, okay? It would not fully be burned out, okay? Or front fire even. It would start projecting forward. This is when you have a lack of oxygen, okay? So you don't have a full burnout of the fuel that's being mixed on the inside, okay? Due to that choking. It's like when you burn wood, the wood would not completely burn. You don't have a blue torch. Meanwhile, when you burn gas, okay, you don't have residues. The gas would fully burn in a blue torch. This is why, by the way, when you look at the engine of the airplane, you don't see fire because it's fully burning. It's fully being consumed. That's almost very clean, okay? Of course, with some toxic gases, but the consumption of the fuel is full. You have full burnout, okay? But when you have a problem, you would start seeing the fire, meaning that the fuel is not being properly combusting. Now, temperature data influences engine control, fuel efficiency, again, icing detection. For example, air density variations due to temperature directly affect lift, correct? So the lift would be affected due to these fluctuations of temperature. Why? Because for colder air, you have a denser, a cold air is denser than the hot air, okay? So it will increase the lift and thus it will affect the performance of the entire aircraft, okay? It will affect also the thrust. So in hot conditions, the aircraft needs to have an increased thrust in order to maintain the same lift. And the climb performance is also affected by these temperature fluctuations or by the changes on the temperature, okay, depending on what temperature you have on the inside or on the outside in the atmosphere, you'd have different performances for the aircraft. Speed measurement, we've already discussed that, but let's read it again. So this is the airspeed indicator, and we've seen how the instrument is made on the inside, okay, the anatomy of the instrument, how you have a diaphragm which is exposed to the ram air that is coming from the inlet of the pitot tube, and when that air pushes against the diaphragm, it will rotate the needle of the ASI or the airspeed indicator. So it's depending on differential of pressures. So the speed measurement in aviation can refer to airspeed or ground speed, which again works in a completely different way. Why? Because it sends a signal towards the ground, and then by measuring the distance or the time it took to go from the airplane to the ground all the way back to the airplane, okay, and by measuring the time and the distance, you can get the velocity, all right? So the airspeed is derived from the difference between pitot pressure, which is the pressure of the ram air, and the static pressure, while ground speed is determined through variations or through navigation systems such as GPS, okay, global positioning satellite. This is how it works, okay? This is basically how the ground speed indicator works. Now, also another type is rotational speed, which is actually the RPM, okay? That is the measurement read by the tachometer. Engine speed is measured using tachometers, okay? Which indicates revolutions per minute, RPM, or percentage of maximum speed in turbine engines. Speed measurements allow pilots to operate within structural and aerodynamic limits in order to avoid stressing the structure or the airplane, or when you have a high speed, or avoiding the stall when you have a low speed. The slow is again when the aircraft can no longer generate lift because the incoming air, the flow of the air around the wings is no longer enough, okay, is no longer within the limits of the acceptable value of the speed, the dynamic speed, in order to lift up the wings, okay? It's no longer flowing with enough momentum, with enough speed in order to generate lift. So speed measurements allow pilots to operate within structural and aerodynamic limits and ensure engines are producing the required power. Position measurement. Position measurement refers to the determination of an aircraft's attitude, which is whether it's banking left or right and how many degrees, because the bank is an angle between the surface of the plane, okay, and the horizontal reference, okay, the horizon, which is parallel to the Earth, the ground surface. And the control surface position, meaning the different controls, whether the flaps, the ailerons, the elevators, and the rudders, their own position. The landing gear status, whether it's dropped or retracted, okay, and navigation position. So it detects the different positions of the controls. So when you have a rotation, okay, and when you're applying a rudder, the rudder adjustment will, like the rudder value to the right or to the left, it will appear, it will be measured. The elevators would be measured, okay, how many degrees, the flaps, so when you apply a flap of 5 degrees, you will see it changing on the display. The ailerons, etc. More than that, okay, you have the attitude indicator, which again present to you whether you're flying level, okay, so if the aircraft is pitched up, this dot here, you see this orange, okay, line on top, it would go above to the part of the blue circle. So here it's pitching up. Now, if it's pitching down, it will go to the brown disk, okay? This indicator, the orange line, it would go to the brown disk. Now, if it's rotating left or right, you see the banking here, bank to the left, bank to the right, and how many degrees. You would have the roll, the pitch indicator, etc. Okay, now, so these are common measurements of positions that are very necessary and important within the aircraft. Now, what are the different devices that perform that within the attitude indicator, which is the instrument? You have, first of all, the gyroscope, okay, like the rotating disc, which is the reference point of the horizon. It keeps rotating, and as the aircraft moves left and right, the rotating disc remains static, okay, it remains horizontal to the ground. That would be the reference on how many angles, how many degrees the aircraft is rotating to the left or to the right. Also, you have, as for the the pitch up and pitch down, the same thing. So as the aircraft is pitching up, you have the accelerometers and potentiometers that resolve that display, okay, to show you, to give you a situational awareness whether the nose of the aircraft is up or down, okay? If it's up, it means it's like this, usually during a climb, but not necessarily during the landing. It would be pitched up, despite the fact that the aircraft would be descending, okay? So it would have a negative descent rate, which is a negative feet per minute, okay? Or during the climb, it would be pitched up, but again, not necessarily. Also, okay, so you have nose down during the descent, okay, during normal descent, but before the landing phase. So modern aircraft increasingly rely on IRS, or inertial reference system, okay? Inertial reference system is what gives you the position on the Earth, okay? Its name is ADIRU, I believe, Air Data Inertial Reference Unit. That would be the device, which is in the Boeing 777, I believe. It's also in the Boeing 787 or Dreamliner, the same device. And satellite-based navigation systems to determine aircraft position with high accuracy, which is very important. Position measurements are vital for flight control, autopilot operation, because the autopilot relies on the measurements to control the airplane. If the measurements are faulty, it can drag the airplane to the ground. Okay, that's why the human factor will always remain important on the inside of the aircraft. Okay, so position measurements are vital for flight control, autopilot operation, and situational awareness. Now, what is the anatomy of the attitude indicator and how does it effectively work? Okay, how does it work? So, at first you have the roll gimbal here, which is when the aircraft is rolling, that would be rotating left and right. Okay, you see here the gimbal rotation. Now, you have in the middle, okay, here you have the horizontal disc, the accelerator that would keep rotating, okay, and that would be rotating horizontally as a reference plane, okay, as an horizontal reference. So as it rotates, it will remain always parallel to the horizon. This is why it is so important, okay. Why? Because you see this, yeah, and it's called a gyro, by the way. Okay, so the gyro, as it accelerates, it will remain always in the horizontal position. Okay, this is something that was discovered in physics. So it doesn't matter whether the airplane is banking left or right. This gyro will always remain on the horizontal position as it rotates at high speed, which is very important. Why? Because we need it as a reference position. So when the aircraft rotates, as you see in the picture here, okay, to the right, let's say to the right, okay, you're standing behind this attitude indicator here, and it's rotating, the aircraft is rotating to the right, okay, like this. So as it rotates to the right, there would be a different angle between this roll gimbal and the gyro, okay, which would steady the horizontal reference arm. Why is it called reference? Because this arm needs to always be horizontal, parallel to the ground at all positions. So the difference between these two, the horizontal arm, okay, and the rotating gimbal, that would give you how many angle you are rolling. You're banking to the right or to the left, so that you can have a situational awareness to know whether you're up or down, or you're rolling, or if you're slanted. Because during night operations, you can never, and especially that the gravity would change based on the direction of the airplane. You can never realize, okay, or understand whether you are on leveled flight or whether you're rolling. So if the aircraft is rolling, you won't even notice it without this instrument. That's why it is very vital. Now, when it comes to pitching up or down, the same thing. So as you pitch up, as the aircraft pitches up, so the noise goes up. However, the gyro will always remain horizontal. Okay, so as the noise pitches up, it would be noticed here. Okay, why? Because this indicator would go upward. Meanwhile, the gyro would be fixed, which is, by the way, this is the orange line here. It's connected to the gyro. It will remain on the horizontal position, the perfect horizontal position. But you would have like this sky, okay? So it will show you as if this horizontal line, which is the reference plane of the aircraft, okay? The reference line of the aircraft, it would go up to this blue area of the disc, the blue and brown disc, which it would indicate to the pilot that the airplane is pitching up. And by the way, it will also give you how many degrees it's pitching up. 5 degrees, 10 degrees, 15. 15 is acceptable, but above, especially for small aircraft, it can lead to a a stall prematurely, especially on high altitudes. Okay, so now when it comes to the roll, we've already explained it. Okay, so both the roll, and these are the degrees for when the aircraft is rolling. So the roll would be measured, and also the pitch up or down. So when it's pitching down, you would have this reference head going downwards. Okay, I'm sorry. The reference, it would be, yeah, like this. This here would go, yeah, the reference head. Sorry, the reference would remain on the horizontal position. However, this line here, this orange line, okay, would appear to be going downward. In fact, the brown area would be going up, which means what? Which means that you are diving. Okay, which means that you are diving. So this area would be going down, okay? Meanwhile, the disk is still on the same position, but this area, this orange area, would be going down. Why? Because the disk position is always fixed by the gyro that's accelerating and rotating on the horizontal plane. So this orange line would go to the brown area, indicating that the plane is in the dive position. I hope it is clear, and sorry if I carried a little bit too long, because it's a little bit complicated sometimes to understand. 2.2 Mechanical, electrical, and electronic instruments. Aircraft instruments can be classified based on their operating principles into mechanical, electrical, and electronic instruments, but they are distinct. Okay, they are completely different, even among, between the electrical and the electronic. Each category has distinct characteristics, advantages, and limitations. Now, for the mechanical instruments operate using physical force or forces and movements without the need for electrical power. So like what we've seen with the altimeter and the attitude indicator and the ASI, okay, you see the instrument, okay, being moved by the air pressure itself to indicate a specific value for the airspeed or the vertical speed or the altitude. Now, examples include the Bourdon tube pressure gauge. Okay, so you have mechanical airspeed indicators, and gyroscopic attitude indicators work this way, mechanically. Okay, they display the values mechanically. These instruments are valued for their simplicity, reliability. They are inherently reliable because everything that is digital and electronic are more prone to malfunction. You can think of your own car. Cars used to be more handy, more practical back in, before 2013. But when the electrical systems started getting into cars and vehicles, especially automation and these things like that, afterwards, okay, the number of faults became more evident, okay, and the system became more prone to different errors, to different malfunctions. Even the cost of reparation became higher, okay, in comparison to a more controllable, more reliable mechanical system that did not use to depend so much on an electronic board, okay, that we call it in for the cars an electrical board, okay, electrical controller. So that's why the mechanical instruments are valued as simple and reliable. However, they are susceptible to mechanical wear out, meaning that vibration can affect them. They can wear out mechanically and break due to friction, due to the gear mechanism being, starting to break down after being used so many times, okay, because there is pressure being applied to these systems. And also limited accuracy compared to more modern electronic systems that are more reliable, more accurate, because computers are usually more accurate when it comes to calculation and measurements. Electrical instruments use electrical signals generated by sensors and transmitters to drive indicators. So we have electrical sensors and transmitters. These are the ones that drive indicators. Okay, examples include electrical fuel quantity indicator. Okay, you have an electrical sensor that once the fuel touches the sensor at a specific level, it will indicate, okay, the fuel is at this level, okay, at 50%, because the sensor is installed halfway depth wise, okay, within the fuel tank. Or you have another sensor on the top when the fuel is, to the top when the tank is completely full. It's at 100% saturation or capacity being filled. It will also light up, which will indicate to you that the tank is completely full, is at 100%. So, okay, also you have the electrically driven gyros that represent the horizontal line electrically. Okay, so electrical instruments offer improved accuracy and flexibility compared to purely mechanical systems because they won't wear out mechanically and they are more like accurate when it comes to mechanical vibration, unlike the mechanical instruments that are susceptible and prone to vibrations and to wearing out because of excess of use. Okay. Meanwhile, the electrical instruments, the problem is that they depend on the availability and stability of the electrical power. So that's why when the main engine that's actually generating power flames out for whatever reason, you would have an immediate loss of instruments during flight. That's why the RAT or the ram air turbine would be deployed in such case in order to keep running these essential and vital instruments so that at least you can, the aircraft can provide some control to the pilot so that he would know whether he's pitched up or down, whether he's banking, especially during the night when you cannot take the external horizon as a reference during flight. Electronic instruments. Now, the electronic instruments process sensor data using solid-state electronics and digital systems. So you have an electronic circuitry going on which these instruments depend for their own measurements. So you have the glass cockpit displays, engine indication and crew alerting system, or ECAS. We've already discussed that. So ECAS is the engine indication and crew alerting system, which is a unified display for engine pressure and temperature, EGT, oil pressure, engine rotation, oil pressure and temperature, and EGT, which is the exhaust gas temperature, especially in the heavy airplanes such as the Boeing. Okay, and you have the electronic flight instrument system, EFIS, which fall into this category. Now, electronic instruments provide high accuracy system integration, meaning you can have multiple displays on one screen, as we've already discussed, and self-monitoring capabilities, which means that this system will immediately notify you when there's something wrong with a value being collected from a sensor. So when there's an overheat, it would alert you, okay? And if there's something extreme going on, it will fire the master caution alarm so that you would be, you would notice what's happening. Another example, like when you have an engine going down, high oil pressure, all of these, okay, for the electronic systems, they have the capability to self-monitor, okay, to monitor all of these indications so that whenever a value is beyond nominal and it's wrong and it's dangerous, okay, it display for you an alert, or also it can also trigger a sound alarm, a sound buzz, so that you can pay attention that something is not going right in order to fix the problem immediately, to troubleshoot. Okay, just like the alarm systems within networking devices and routers and these other things, just like when you have different types of devices or computers, your computer displays errors. The same thing is for the electronic instruments. Okay, it detects errors and then displays them on the screen. So electronic instruments provide high accuracy, system integration, self-monitoring capabilities, and advanced failure detection. So they can detect failures or values outside of nominal acceptable values in an advanced, more intelligent way. Their complexity, however, requires robust redundancy. Why? Because if something fails within the display, multiple displays can be, lost altogether. Okay, so we need redundancy and protection against electromagnetic interference. You need to have redundant, displays, redundant devices, instruments, so that you can back it up, because the electronic display is susceptible to faults. Like, it can itself be at fault, or it can be prone to being affected by electromagnetic interference and no longer work properly. Accuracy, precision, reliability, and errors. Now, understanding measurement quality is essential when interpreting aircraft instrument indications. Okay, several key terms describe instrument performance. So at times you would have an excursion, a different value, okay, a difference or a gap between the actual value of a parameter being measured, such as the airspeed, okay, within the airspeed indicator. So you'd have a difference between the airspeed being displayed and the actual airspeed, which is the actual speed of the airplane. Also, in the same way, you would have a difference between the magnetic north and the perfect north when we're talking about the heading of the airplane. Okay, so the direction of the magnetic north is different than the perfect north. So you would have the excursion when it comes to the directional gyro, okay, the heading of the aircraft. So here is why we need to talk about these indicators or these differences, because when we talk about accuracy and precision, this will affect the performance of the aircraft altogether. And it's not only for key instruments, it's actually everything, okay? When it comes, it's not only for like the heading and the ASI, it can be also like the engine power, how it's running, if it's measuring correctly the EGT, okay? You might have faults within the indicators at times, okay? Like if the RDS, the resistance display, okay, for the thermal display, for the resistance, if it snaps, it will indicate fire. Meanwhile, there is no fire. Like the resistor itself had broken. So let's start with accuracy. Accuracy describes how close a measured value is to the true value of the parameter being measured. Okay, so it would be the measured value minus the actual value divided by the actual value. That would be the error rate. Okay, so 1 minus the error rate, it would give you the accuracy. Let's say you have a measurement of 3. Let me try to write it. You would have a measurement. I'm not able to access the pen, I'm sorry. So 3 is the actual measurement, or the current measurement, but the actual value is 4, correct? So the error would be 3 minus 4 divided by 4, which is the real value. It's 1 over 4, which is 25%. Okay, so the accuracy would be 1 minus 25, or 75%. An instrument can be precise but inaccurate if it consistently provides the same incorrect reading. Okay, so it's precise, meaning it's always performing in the same way. However, its own performance is inaccurate. Okay, the precision is the ability of reproducing the same results over and over, so it's consistent. However, that precision does not mean that the measurement is accurate. Okay, because you have a constant error rate always, so you need a correct adjustment so that it can measure well. Okay, now precision refers to the repeatability or consistency of measurements, as we mentioned. High precision means that the instrument reproduces the same readings, the same values, under the same conditions or circumstances. That's the important point. Reliability. It is the ability of an instrument to perform its intended function over time without failing. This is what reliability means. So, the aircraft instruments must meet strict reliability standards, okay, after stress testing and different tests. They need to withstand all of these tests to prove their reliability, to prove that they are consistent, that they can outlive different conditions of stress, of high pressure, of extreme operating limits, such as under hot temperatures, hot weather, under icing, okay? They need to survive that so that they can be reliable during the flight. They can be trustworthy, and because the pilot depends on them for correct readings, okay? So it is critical to have safety there, okay, and the correct values being read. So they need to meet strict reliability standards due to the safety critical nature of their operation, because all of the decisions made by the pilot are based on the readings of these instruments. Measurement errors. Errors in aircraft instruments can arise from multiple sources, including mechanical errors due to friction, electrical interference when we're talking about electrical instruments, also temperature effects, because the temperature, by the way, can create noise, especially in receptive systems like an antenna, receiving antennas, and different electronics. The change of temperature can change the different value of impedances or the resistance of different components, leading to errors in reading. Okay, but also you have the aging components. So when some components, especially electronic components such as resistor, capacitor, wear out, it would start, leading to erroneous readings, okay, to error readings, and also environmental conditions. So when you have changes in the temperature, or especially the icing, can affect the instruments so badly at times, okay? So it could affect the accuracy. At times, the performance altogether is affected, not only the accuracy, but the operability of these instruments. Now, when it comes to mechanical friction, it can affect the rotation of these handles when it comes to these instruments that we've spoke about earlier, such as the ASI, the altimeter, and the VSI. So, errors are commonly categorized as systematic errors, random errors, okay, and gross errors. Understanding these errors allows pilots and maintenance personnel to detect abnormal indications and take corrective measures or actions. Now, if we want to talk a little bit about these three types of errors. So, systematic errors, we would be talking about something within the system, within the instrument, okay, that is systematic, due to a malfunction, due to a component that is no longer correctly performing and allowing a good reading, an accurate reading to be carried out. For example, a resistor, a capacitance, a diode has worn out, so it would lead to an error within the measurement, like a resistance that has broken off, that measures the temperature. It would display an overheat. Why? Because it has suddenly become an open circuit. Okay? So it would be something within the instrument or the sensors. That would be the systematic errors. Or, for example, the mechanical attitude indicator or altimeter or the VSI, the handle broken, or the gyro, okay? The horizontal gyro or accelerometer would be stuck in some way, so it would lead to error in reading. Let us not forget that you have the friction problems, you would have electrical interference, all of that. Okay. Now, random errors can be random, like for example, when we talk about electronic system, okay, you have a binary system that becomes in display as converted to system of numbers when it comes to readings of different instruments. So it can be fault, a binary fault for some reason that would lead to an error value, okay? Or it would be a component that at times it's defected, okay, but then it becomes back, it becomes like active. For example, there was a problem once on Turkish airline where you had, I think it was in the attitude indicator, okay, and the altimeter, which is an integrated instrument. So they had a break in the circuit. So at times, due to the vibration, the circuit would be separating. It would show a false reading of the altitude, which is, by the way, this reading is what the autopilot depends on in order to guide the airplane when it comes to the landing. So at times it would break, it would show false readings of the altitude, and at times due to vibration it would go back and rejoin the circuit. So that broken circuit, it would contact again, like it would get in contact again on both sides, so it would appear to be working. Why? Because the current is now working, like penetrating properly through this conductor. Okay, so at times due to vibration it would separate, acting as an open circuit on the plate, this electronic plate. At times it would be working properly. Why? Because it's touching and separating. Okay, so this led to false measurements. It brought down an airplane. So again, that would be a kind of random errors. And finally, you have gross errors, like errors that are not only systematic, they are large scale errors, okay? They are multiple things together or on a large scale, something vital affecting the instrument, okay? It's not a minor fault, it's something vital, all right? So we need to understand these errors and the scale of these errors. What systems do they affect in order to be able to troubleshoot and also understand what's happening, and on the ground to replace the part that is malfunctioning with a new part to fix the problem. 2.4 Instrument calibration and limitations. Okay, let's talk about instrument calibration. What is calibration? Calibration is the process of comparing an instrument's output with a known reference standard and adjusting it to that standard in order to maintain accuracy in measurement. Okay, as an example, when we talk about the altimeter, you need to adjust the altimeter to set it at 0 meter, and this would be on the ground level. Okay, we set the air pressure of the static, compartmentalized air within the altimeter. We set it to the air pressure on the ground when the aircraft is still on the airport. That would be the reference pressure, okay? And that would be the 0 meter height of the airplane. From that, okay, now, based on that kind of reference, the aircraft, when it climbs in the air, it would be able to accurately measure its height in reference to this static pressure, which is the pressure of the air when the height was 0. This is how the diaphragm within the altimeter would be expanding, okay, in reference to the external air, which of course it will have its own pressure decreasing as the aircraft climbs. But as this external pressure decreases, you would have, due to the differential or the difference between the static air on the ground and this external ambient air, a correct reading of the current altitude. This is why we adjust or we calibrate, okay, the altimeter on the ground. The same thing for the airspeed, the same thing for the entire pitot-static system. Why? Because all measurements shall be done in reference to that point on the ground, to that current air pressure. Okay, now if you go into a different zone, you would have a different calibration for the air pressure based on which you can get accurate, fairly accurate measurements. Okay, now aircraft instruments are calibrated during manufacturing, maintenance inspections, and after repairs. After repairing. Now, regular calibration ensures compliance with regulatory requirements and maintains measurement integrity. Okay, meaning the measurement should be transparent, should be correct throughout the instrument's service life. Instrument limitations. All instruments have inherent limitations. This may include response time delays, meaning that the value won't be real time. Okay, there would be a delay between the actual value of the air pressure, for example, or the current altitude, and this value being updated on the instrument. It won't be indicated immediately. There's a lag between the current altitude of the airplane and the displayed altitude, to make it simple. The same thing goes for other instruments, but when it comes to the altitude, this is one of the most common problems, or the most common examples where you would have a lag between the current value and the actual displayed value. Also, you have limited operating ranges, meaning that for some airspeeds, they won't be displayed on the indicators. Okay, you have sensitivity to environmental factors, so sensitivity to different like changes, like fluctuations and sudden changes in air pressures can falsify the current data being collected. Why? Because it's actually, the aircraft is actually depending on these variables, on these values, okay, to display the current airspeed, altitude, VSI. So changes in air pressure would change these values and display something that wouldn't be accurate at the moment. Okay, even if it's momentarily, it won't be an accurate value. It can be a little bit confusing at times. And also dependence on power sources, meaning that for especially electrical instruments, you would need a consistent power coming from the engine to have an accurate display. So if you have a power cut or an electrical problem or of some sort, or a short, okay, it can give you a false alarm, a false measurement, etc. Now, pilots and engineers must understand these limitations to correctly interpret instrument indications and avoid unsafe operating conditions, meaning making decisions based on false premises. Instrument limitations are documented in aircraft manuals and certification data so that you can follow these guidelines in order to try to understand and interpret a problem when it doesn't make any sense. This is why you go through a checklist when a false alarm fires. It might be false, it might not be, or when you have like an instrument acting up and you don't understand what's happening. That's why we need to go down the checklist. Now, operational awareness, effective use of aircraft instruments requires not only technical accuracy, but also human awareness to understand quite clearly how they work and why at times they might be displaying values that do not make any sense. We need to understand how they operate. We need to be aware, for example, of the lag, the delay between the actual altitude that you're hitting with your airplane, the actual level, and the altitude, the value of the altitude being displayed on the altimeter at that moment. Okay, so cross-checking multiple instruments, we need to do that, and understanding system behavior under abnormal conditions are essential skills for safe flight operations. For example, we need to verify and cross-check the behavior of the VSI and the altimeter to make sure that they are both positive, indicating a correct climb rate, and also the nose along with the pitch. Okay, if you're pitching 5 degrees and the aircraft is not climbing, you might be entering into a stall soon, And in order to verify that, you need to also be checking the ASI, because at low speed, the aircraft would no longer be climbing. It can enter a stall, which will degrade its lifting capabilities, and that's when you need to correct it, okay, before even the sounding of the stick shaker. That would be the alarm for that that's about to happen.